Assalamualaikum warahmatullahi wabarakatuh and good afternoon. Hello guys, hi girl. How are you? I hope you are in a good conditions. Welcome back to campus. Okay, today we will continue the course of introduction of thermodynamics. Today's topic is about second law of thermodynamics. Okay, this is chapter number 4. So, first of all, I would like to make the acknowledgements to those of my cliques in UITM Shahalam because of their efforts to come out with these slides. Thanks to Dr. Idris Saad and also Dr. Al Hassan Salami Tijani and also to Dr. No Afifah Yahaya. So, our topic in chapter number 4, uh, we will be covered on the 4 subtopic. This is part 1, chapter 4. So the sub topic is will be covered is thermal energy resolver, heat engines, engine conversions efficiency. Number 2, refrigerators and heat pumps. Number 3, reversibly and irreversibly processes. And the end of part 1 for chapter 4, I will show or discuss with you about the Carnot cycle and principles and also the Carnot heat engines. Actually, the objective of this topic of chapter number 4, student, that's mean you have to or you should be able, okay, you should be able to know the introductions of the second law of thermodynamics, of course, because this is a chapter about second law of thermodynamics, and you also have to identify, okay, you should able to identify valid processes of those that certified both the first and the second law of thermodynamics. Then we will discuss, or student, you should able to discuss, okay, thermal energy resolver, reversibly and irreversibly processes, heat engines, refrigerator, and heat pumps. You also must able to describe, okay, you also must be able to describe the Kelvin, Planck, and Clausen statements of the second law of thermodynamics. Then you must also know or should be able to apply these second law of thermodynamics to the cycles and also the cycle device. Uh, you also should be able to discuss the Carnot cycle, examine the Carnot principles, idealize Carnot heat engines, refrigerators, and heat pump. And at the end of this part 1, student must be able to determine expression for the thermal efficiencies and coefficients of performance for reversibly heat engines, heat pump, and also the refrigerator. We look on the definitions of the second law of thermodynamics. Actually, what is the second law of thermodynamics? Previously, uh, in the first or the in the start of the semester, you have been discussed, you has been introduced the first law of thermodynamics. That means provide the basic definitions of internal energy associated with all thermodynamic systems, and also the system and also the state that rule the conservations of energy. Okay, but in second law, it is actually concerned with the directions of the natural processes. These exerts that a natural process runs only in one sense, not in not reversibly. Example, we take heat. Okay, heat always flow uh, spontaneously from hotter to colder bodies, and we know it never been reversed unless external work is performed on the system. So its modern definitions for in term of entropy. Okay, so the modern definition is in term of entropy. So this is pictures or figures, uh, how we define the second law of thermodynamics. That is the one-way processes, and it occur in the natural processes. So in the actual thermodynamic process, a process must satisfy both the first and second law of thermodynamics to proceed. Okay, this is the diagram how we this describe the process in actual thermodynamic process. That means first and second law um, must be certified. Okay, the measure of the second law have three reasons. Okay, why we have to study the second law. So the first one, this law, the second law, may be used to identify the directions of processes. And number two, the second law also assert the energy has quality as well as quantity. Uh, as you know, the first law is concerned on the quantity of energy and the transformations of energy from one form to another with no regard to its quality. But in the second law, it provides the necessary means to determine the quality as well as a degrees of degradations of energy during the process. And number three, why we must study or we must know the second law is it also used to determining the theoretical limits for the performance of commonly used engineering system, such as heat engines, refrigerators, and as well as predicting the degree of completions of chemical reactions. Okay, this is the major use of the second law. So these number one, two, and number three show the figures that reflect with the users to know of the second law of thermodynamics. Okay. The development of the second law of thermodynamics is very convenient to have the hypotheticals of thermal energy resolver or just a resolver. So what actually is a thermal energy resolver, or sometimes we call it as a reservoir. So it is a body with a relative large thermal energy capacity, mass at specification heat that can supply or absorb finite amount of heat without undergoing any change in temperature. There are two types of thermal energy resolver. It's called source, and another one is sink. So, what is source? Source actually supply finite amount of heat without undergoing any change in the temperature. And sink is absorb finite amount of heat without undergoing any change in temperature. So in practice, for the large body such as a sun, oceans, lakes, rivers, as well as a atmospheric air, we can model this accurately as thermal energy resolver because of their large thermal energy storage capability or thermal masses. Okay, we go for the heat engines. Okay, uh, the thermal energy resolver or resolver can be simply modeled as heat engine. So you have been defined definitions of the resolver, uh, source and sink. And when we want to more understanding this resolver, we can simplify model it as a heat engine. Okay, the figure as the heat engine is shown at the right side. Okay, these figures. So heat engine actually employ a range of methods to apply the heat and to convert the pressure and volume changes into mechanical form. That means it's convert heat to work. That is heat engine. So actually, heat engine involve four processes to convert heat to work. Okay, so it have high temperature source. It will go to the low temperature sink, and heat engine, the high temperature will turn. Okay, they will turn the rotating shaft, and this shaft will provide work to the environment, and then the heat engine will reject the high temperature that have been come from go to the heat engine and reject to the low temperature sink. So four processes that involve with the heat engine. Number one, they receive heat from the high temperature source, such as solar energy, oil furnace, neutral reactor, and then they convert part of this heat to work, usually in the form of rotating shaft, and then they reject the remaining wave heat to a low temperature sink, uh, to the atmosphere, river, etc. And lastly, the operation must be a cycle. Heat engine and other cycle device usually involve a fluid uh, to or form with heat transfer while undergoing a cycle. Okay, and this fluid actually called as a working fluid. That is a working fluid. That's why in the chapter number 3, when you are uh, given a case or cases, problems to solve, firstly you have to look what is the working fluid of that device. So from there, you will know how to solve that problem. Okay, this is a fluid that we call the working fluid. Example of every heat engine involved include the steam engine. And steam engine actually is a external combustion engines, and this is the most of the world power plant use, okay, as steam turbine, a modern form of steam engine. So for the internal combustion engines, it will call as a gasoline, petrol engines, diesel engines that have in the automobile or the truck. Okay, but the steam engine will it is in the type of the external combustion engines. The work providing device that best fit into the definitions of heat engine is the steam power plant. So this is the pictures or the figures or the devices that involve with heat engines or steam engines. Okay, it have a turbine, a condenser, a pump, and also a boiler. So the boiler actually provide energy source, and then it will goes to the turbine and turn the turbine to produce work, and then the waste heat come out from the turbine will get to the condenser, and from there the heat will be rejected, okay, from the condenser to the atmosphere, and from there pump will absorb or pump will suck the working fluid such as water, and then push this water or working fluids to the boiler. Okay, so Q in actually, as you see here, Q in is the amount of heat supplied to steam in boiler from the high temperature source. Q out at the condenser is the amount of heat rejected from steam in condenser to the low temperature sink. And work out actually provide from the turbine is the amount of work delivered by steam as it expand in the turbine. And work in actually at the pump, amount of work required to compress water to boiler pressure. Okay, that is the heat and work that have in this steam engine. So when we want to find the network of this the system, you can determine the work out minus work in, and this is in unit joules. Uh, Also, you also can find the work net from heat. That's mean Q in minus Q out. You also can get this amount in the unit of joule. This is for heat engine. Okay, to know the powerful or the output of the engine or heat engines, we come to the thermal efficiency. Okay, based on the cycle of the steam power plant and the third major use of the second law of the thermodynamics, the magnitude of energy used in order to complete the cycle of the performance of the plant can be measured. So this is some of the elements, the important elements in thermodynamics. Uh, you want to calculate the measurement called thermal efficiency, and we can express this thermal efficiency in mathematical form by using the formula of desired result divided by required input. So for the desired result, you look at these figures. what happened, desired result is the net work output. Okay, and the required input actually is a total heat input. Okay, and then from there we put work net over Q in because total heat input is Q in, and how to get work net? Work net come from Q in minus Q out. So simplify, we can have the thermal efficiency is 1 minus Q out over Q in. Okay, this is the picture. Or you can get these uh, calculations also based on the heat engines. Okay, heat engines, where as you see previously, heat engine is receive high temperature reservoir source, uh, and then it will uh, produce work net, and then all the waste will push out to the low temperature resolver. So from there, work net can be calculated based on Q high minus Q low, heat at high temperature minus heat at low temperature. That's we get the W net out. And for the thermal efficiency, work net over QH, and simplify lastly, the formula will become 1 minus QL over QH. That is the mathematical writing for the thermal efficiency. Okay, now let's look on the second law of thermodynamics, Kelvin plug statement. Okay, what is Kelvin plug statement? Actually, Kelvin plug statement is related to the heat engines. Okay, what it say? It is impossible for any device that operates on the cycles to receive heat from a single resolver and produce a net amount of work. Okay, that is the statement of Kelvin plug. Uh, what is mean? Okay, it means no heat engine can have a thermal efficiency of 100%. Or as for a power plant to operate, the working fluid must exchange heat with the environment as well as the furnace. So the third major use of second law of thermodynamics, when you see the use of thermodynamics number 1, number 2, and number 3, this is for number 3. So it is impossibility to have 100% efficiency heat engine is not due to the frictions or other dissipative effect. It is a limitations that apply to both of the idealized and the actual heat engines. So that is the statement of Kelvin plug. Okay, so you have to understand this statement because this is related to heat engine. Okay, remember, not all heat engine can have a thermal efficiency 100%. Okay, let's do the example of heat engines. Okay, it give these examples or the problems. It said that a steam power plant produce 50 megawatts of network while burning fuel to produce 150 megawatt of heat energy at the high temperature. Determine the cycle thermal efficiency and the heat rejected by the cycle to the surroundings. Okay, number one, it want you to find thermal efficiency. Number two, find the heat rejections of the cycle. Okay, to solve the problem, you have to remember the thermal efficiency for the steam power plant. Steam power plant actually is the heat engines. So the thermal efficiency is W, or the work net out over Q in, or Q at high temperature. So it give the steam power plant produce. Okay, it produce 50 megawatt. Okay, 15 megawatt of network. So that is a word net. So Q in is it's burning fuel to produce 150 megawatt. This is Q in to the system, or Q at high temperature of heat engines. So put in the formula, and then you will get 0.33 or astronomically 33.3%. This is the thermal efficiency of this system. And in this question, it also want you to find the heat rejection by the cycle to the surrounding. To find the heat rejection, you know the work net of this system, and also you know the formula that can use to find work net is QH minus QL. So from here, it want you to find heat rejection. That's mean Q at low temperature. So you restructure these equations, then you will get QL at a low temperature is 100 megawatt. Okay, got it? Can I continue? Okay. Okay, this is another problem. Maybe you can make as an exercise by yourself. Okay, do the training calculations. And this is example problems sample. So do it yourself to calculate this, or do the solution to make the solutions for your practice. Okay, now we go for the refrigerator and heat pump. What is refrigerator and heat pump? It is a machine or device that move heat from one location to another location using mechanical work. That is refrigerator and heat pump. And this it convert work to heat or heat engine operation in reverse. Okay, this is diagrams, or this is of pictures of devices that have in the refrigerator or in the heat pump. Okay, it also have 4 devices: condenser, compressor, evaporator, and expansion valve. So this system, this refrigerator or heat pump, move heat from a lower temperature source to another of heat temperature sink using mechanical work. Okay, in natural, you know heat is transferred from the high temperature medium to a low temperature once without requiring any devices. That is for the natural. But for refrigerator, it is to maintain the refrigerate space at low temperature by removing heat from it. So how to do this? We need some devices or some energy that will move this energy from low temperature to high temperature. For heat pump, it is to maintain heated space at the high temperature. The concept is as same like as refrigerator, but the functionable is different. Okay, refrigerant and heat pump. So for this refrigerant and heat pump, the performance that you want to find, or the measurements that you want to find for this system is called COP. Okay, coefficients of performance. So to find the efficiency of this refrigerator, let's look on the left sides of the figure. So this is a refrigerator from cool space. Heat has been removed to the hot or warm environment by using refrigerator that have four devices. Okay, so to do this movement, we need work in to the system. So the COP for refrigerant is desired output over required input. This is general equations for efficiency. Desired output over required input. So look at refrigerator. What is the desired output? So the desire is to make it more cool. So QL, okay, heat at low temperature. Required input is work net. So you know the work net is QH minus QL, and then put in the equations, put in the formulas, then lastly you will get simplified. This formula will become 1 over QH over QL minus 1. That is for refrigerator. For heat pump, the objective is supply heat to the warm space. So cool, and it want to supply heat to the warm space, but the difference between refrigerator is the desired output. In this heat pump, the desire is QH. So we put QH at desired output. Required input is work net. So then solve this formula. Then we will get COP for heat pumps is equals to 1 over 1 minus QL over QH. And simplify these equations will give COP HP is equals to COP refrigerant plus 1. Okay, that is the difference between refrigerator and heat pump in terms of efficiency, or we call it as a COP, coefficients of performance. Okay, now we look on the Clausen statement. Okay, actually Clausen statement is related to refrigerator and heat pump. Kelvin statement related to heat engines. Okay, what is Clausen statement? It says that it is impossible to construct a device that operates in a cycle or produce no effect other than the transfer of heat from a lower temperature body to a high temperature body. That is statement of the Clausen. So what it means? So it states that the refrigerator cannot operate unless a compressor is driven by an external power source, such as electric motor. That is it. That's its mean. Okay, that's mean we want once when you want to operate this system, you have to put external power source. This way, the net effect of the surroundings involve the consumptions of some energy in the form of works, in addition to the transfer of heat from the cooler body to a warmer one. So to date, that means until now, no experiment has been conducted that contradict with the second law, and this should be so we can take it as a sufficient proof of its validity for this Clausen statement for refrigerator and heat pump. Okay, now we look on the equivalence of these two statements, Kelvin and Clausen. Okay, so when you look the figure left and right, we can say that any device that violates the Kelvin plug statements also violates the Clausen's statement and vice versa. So this actually statement can be used as same as both. Okay, the Kelvin and the Clausen are equivalent in their consequences, and these their statements can be used as the expression or the second law of thermodynamics. Okay, when you look this refrigerator, in this refrigerator, this is for Clausen statement. This is for Kelvin plug statement. So it have a syn process. Okay, it the process or the way of the process is equivalence. That's why we can say it, or we can both say it. These two statements valid for the second law of thermodynamics. Okay, looks on the sample problems. Okay, the food components of the refrigerator is maintained at 4 Celsius by removing heat from it at a rate of 360 kJ per minute. If the required power input to the refrigerator is 2 kilowatt, determine the COP of the refrigerator and the rate of heat rejection to the room that causes the refrigerator. So to do this, to solve these problems, so the power consumption of refrigerator is given. So assumption we have to make this is a steady operation conditions. Then the analysis will firstly come from the coefficient of performance equations. Okay, so for refrigerator, COP refrigerator is Q dot L over W dot L, because dot here, if you have a dot at upper, so you must have a dot at lower. So dot means rate. Okay, this is a rate. The unit for the formula joule per minute. So Q dot L is 360. Work dot rate of work is 2 kilowatt. So uh, you put the value in the equations, then it gives 3. The COP of the refrigerator is 3. So 3 kilojoule of heat is removed from the refrigerated space for each kilojoule of work supply. Okay, because with this amount of value energy that given, only 3 kilojoule of heat is removed. And then it want you to find the rate of heat rejections to the room. So you know the formula, work net is equals to Q dot H minus Q dot L, and then restructure these equations to find Q dot H, and then put the values. From there you will get 480 kilojoule per minute. Okay, this is how you calculate the COP and the rate of heat rejection. Okay, this is how the problem how did the problem show. Okay, this is a refrigerator. Then Q dot L, that means heat, low temperature, being pushed to the kitchen, but using work that supply to the heat pump. Okay, another problems, try do yourself. Okay, try to solve by yourself. reversible and irreversible processes. What is reversible and irreversible processes? For reversible, it is a process that can be reversed without leaving any trace on the surrounding. And for irreversible process, it is a process that is not reversible. Okay, this is a two different things. Okay, actually, in natural, what we have learned before at the first slide, in the first chapter 4, all the process is in a one-way process. That is irreversible process. But when you want to make the analysis as an engineer, you need a reversible process. So, irreversible process, we can categorize it as a actual process. But for reversible process, we can typical it as a ideal process. So, as you all know, all the processes occurring in the natural are irreversible. Why are we interested in reversible processes? Number one, they are easy to analyze. Number two, they serve as idealized model, that means theoretical limits, which actual processes cannot, sorry, as actual processes can be compared. Some processes are more irreversible than others. So why we try to approximate reversible process? Why? As I said just now, as the engineers or as the professionals engineers, we need to analyze some of the projects, some of the design that needs to approve the concepts of reversible process. So let's see the example, the figure 629A, frictionless pendulum. It is as a two familiar reversible process. B, quasi-equilibrium expansions and compressions of a gas. These two is examples for the reversible process. And if you see at the bottom, the reversible processes deliver the most and consume the less work. That is important to know because that's why we need or we will love to know the reversible process because when we assume the system is on a reversible process, these processes can deliver more or the most work and it also consume a little or a less works for the system. As you see, a slow reversible process happened when as expansions and compressions for the water. Look at the pressure distributions. So here for the slow reversible process, the water is constant. The water is in the cool conditions. But for the fast irreversible process, what happened? The water is on the non-Cauchy equation. That's mean in not at the constant state, but the pressure distributions is less, and also for compressions, the water is irreversible, and the pressure distribution shows more on the compressions at the fast irreversible process. Okay, we continue for irreversibilities. Okay, what is irreversibilities? That actually this term is actually for the factor that cause the process to be irreversible. Okay, so they include frictions, unrestricted expansions, mixing of two fluids, heat transfer across a finite temperature difference, electric resistance, inelastic deformations of solid, and chemical reactions. The presence of any of these effects renders a process irreversible. So this is a factor that affect the irreversible processes. Okay, look for the example for the frictions. Frictions render a process irreversible. Okay, if you look on the system that consists of the cylinder and the pistons and the gas, there is a frictions in the along the cylinder and across the piston, and this is made it the process is irreversible. It is also can see in the soda uh, can. Okay, so heat transfer to a temperature difference is irreversible. The reverse process is impossible. If you look on B, the outside temperature is 20 Celsius, so heat cannot go out from the system, from the can to outside the surrounding. Okay, actually heat will go naturally irreversible to high to low temperature. Okay, so in this case, the heat inside the can soda cannot come out to the surrounding. That is impossible. Okay, and another example is irreversible compressions and expansion processes. So if you look here, A, B, and C, A is a fast compressions, B fast expansions, and C is a unrestricted expansion. So these are the example how uh, we can show the uh, viewing of the irreversibly sorry irreversible process. Okay, next let's know about the internally and externally reversibly processes. Okay, if no reversibilities occur into the boundaries of the system during the process, so we call it as the internally reversible process. Okay, when if no reversibility occur outside of the system boundaries, so we call it as externally reversibility or externally reversibly. Okay, when inside and surrounding is no reversibilities or not involve any of the factor called irreversibilities, so it is totally reversibly process. So a total reversibly process involves no heat transfer through a finite temperature difference, no non-quasi equilibrium changes, and no frictions or other dissipative effect. Okay, this is what you have to know. Okay, when you want to make the analysis in the thermodynamics based on second law uh, of the thermodynamics. So this is some assumptions that you have to know or you have to come out when you make the analysis involved with a reversible process. Okay, that's all for part one, chapter 4, second law of thermodynamics. I hope you will gain some of all the knowledge or some of the knowledge that I have give you during this lecture. Uh, See you in the next lecturings. Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh and good day. Bye bye.